Okay. Hello, everyone. We apologize for being 8 minutes late. Um, we strongly apologize for that. So today we are at our fifth KmerAI talk, and today we will be discussing a topic called detecting Android malware with convolutional neural networks and Hilbert space filling curves. And then we will be having as guests today, not one but two people. Uh, why am I hearing myself? So our first guest is Mbungang Ngaibe Benedict, a PhD student um, at the University of Ngaoundere, working under the supervision of Professor Franklin here. We might have an issue. I would like anyone who is connected via the StreamYard link to instead go online on the YouTube page and not the StreamYard link. The StreamYard link is mainly for the speaker. Thank you. So, Benedict, just one question before I give you the floor. Do you want to have questions while they are coming, so during your presentations, or you want to have them at the end of your presentation?
Yeah, I would prefer to take them while I'm presenting.
While you are presenting. Okay, so
Yes.
then if there are questions that pop up in the chat, I will then have to maybe stop you and tell you about the question so you can answer. Is that okay?
No, yeah, no problem. No problem. Thank you.
Okay, perfect. So now I give you the floor and please go ahead.
Okay. Good evening, everyone. As the presenter said, the moderator said, I am Mbungang Ngaibe Benedict, a PhD student at the University of Ngaoundere, and our topic for discussion this evening will be on detecting Android malware with convolutional neural networks and Hilbert space filling curves. We are going to follow this plan for the presentation. We'll have an introduction. We would look at the context. Then we will go to look at the methodology. We'll look at the results and discussion. We'll look at the conclusion and perspectives. So for the context, there has been a significant increase in the momentum for malware detection and mitigation efforts, driven by the rapid spread of mobile malware and the growing adoption of smartphones and electronic tablets worldwide. As we know, Android operating system has a dominant market share of about 70.19%, making it the leading source nature of the platform and fragmentation of the Android ecosystem, which creates vulnerabilities that malware can exploit. According to Kaspersky Security Network report, about 4.9 million malware attacks were detected in the first quarter of 2023, underscoring the severity of the problem. Also, we have the Cybersecurity Ventures, another agency, estimates that in 2023, the total annual cost of malware damage was expected to exceed $6 trillion US dollars globally, highlighting the substantial economic impact of this threat. It is important to note that conventional signature-based malware detection approaches have failed to cope with the rapid growth of mobile malware and face limitations in uncovering novel attack variants or types, as they often rely on predefined patterns matching known malware behavior. Also, the combination of the rapid growth in the mobile device usage, the dominant market share of Android, and the inherent security challenges, and also the staggering financial consequences of malware attacks, has created an urgent need for robust and effective malware detection solutions. So this has prompted researchers and security experts to be working very hard to develop innovative approaches to address this growing threat, with focus on techniques that can accurately and efficiently identify Android-based malware. Among other solutions, artificial intelligence stands out because it has shown promising results in identifying malware. Android apps can now be transformed into images and given to excellent image classification AI models to spot patterns and anomalies that can be used to identify malware. However, representing Android apps as images to be used for malware detection is not straightforward. It has been noticed that most convolutional neural network models, which are AI models that are widely employed for image-based malware detection tasks, are designed to work with fixed input sizes. So this makes it difficult. This makes it challenging to generate images that fit these fixed input sizes, and such images that are generated to match what these AI models demand can lead to distortions and information loss, as the original byte-sequence structure of the Android app is not preserved. Consequently, the detection accuracy of Android malware classification models may be negatively affected. So we on our screen, we want to show you the traditional way which images are generated prior to being used for Android malware detection. And we are saying that this traditional way that most papers that we've seen in the literature are using, it has a problem. That's what we are trying to see. The way these images are generated traditionally has a problem. And that problem, as we said in the previous slide, is that when they are generated using this method, there is some distortion. What we take from the app to use to transform as an image, there is some distortion in that generation process, and we have noticed that this distortion can lead to problems of accuracy in the malware classification models. So on your screen, you have an algorithm, the algorithm that is normally used by most papers that are using this approach for malware detection, this image approach. This is what they use. This is the algorithm that they use to generate their images. To illustrate this effect, on our right, I don't know if you're seeing my screen, we have the app binary code, which is normally a sequential file. And the idea is to transform this file into an image using an image generation algorithm. As we can see, if we follow the traditional image generation approach, there will be some distortions which are shown on the left. We have byte sequences which appear on different rows. You see them mixing up. This distortion can have an effect and impact on the overall performance of the AI model that is being used to classify, based on these images, to classify apps as being malicious or benign. So our main objective of our work was to propose an Android malware detection approach that limits or minimizes the effect of the bytecode distortion while generating images from this bytecode. So, as a specific objective one, we were looking forward to develop a comprehensive, systematically structured review of existing approaches using image-based techniques with machine learning and deep learning. We had to review what has been done in the literature to understand the current state of the art with regards to the problem we want to solve. Our second objective, which will be our point of focus for this presentation, was to propose an approach that uses the Hilbert space filling curve to characterize the behavior of Android applications by mapping app bytecodes to 2D grayscale images while maintaining their spatial locality. We are going to be telling you why our choice of the space filling curves. Okay. Of course, our work is justified by this review that was carried out in 2020 by Kai-Jun Liu and all, which, if we follow the review, they highlighted the fact that feature extraction from raw data sets can often lead to problems such as inconsistent specification, redundancy, missing values, and imbalanced distributions. They emphasize that such issues with the input data can undermine the reliability of machine learning models, and therefore data pre-processing is a crucial step to ensure the effectiveness of these techniques. So our problem lies in this domain of data pre-processing issues, which can impact the overall performance of machine learning models. Specifically, we are looking at problems that are related to generating images from Android applications and using those images to classify apps as malware or benign. So they went further to say, we noticed that despite the publication of Kai-Jun Liu and all, many of the studies included in our literature continue to exhibit this very shortcoming in their image processing methodologies. So that's why there's a need. It justifies why we had to carry out this study to fill this gap, which we noticed in the literature. We have some background. It's important for us to understand the Android text file structure, which is the main artifact that we used in this our approach. Android distributes its applications as APK files, and an APK file is a zip file, and one of such files in the APK files we have the manifest file, we have libraries, we have resource files, and we have text files. So these are some of the main resources which we find in the Android application package kit, which is the main format which Android uses to distribute and install applications. So we are going to be interested in the text file, which contains the executable code for files. We are interested in the text file because that is where the behavior or the logic of the application is found. So this is it's the structure of our DEX file. It has a header, a string section, maybe ID section, make of the string type, prototype, and we have a data section. It is also important for us to understand what space filling curves are. And they are mathematical functions that are capable of mapping a one-dimensional domain into a multi-dimensional range. In our case, we are interested in mapping, let's say, a line into a two-dimensional space. We are going to see more. They are so many examples of space filling curves, but we are going to be interested in the Hilbert. It is the space filling curve that has mostly been used, and it has properties that is going to help us generate our image optimally. So the Hilbert curves is notable due to its diverse applications. It can be used, it has been used in the past for other purposes in the domain of databases, in the domain of imaging, which we are also going to use it, and in many other domains. So here on the we have the algorithm that is used, the recursive algorithm for to generate the Hilbert curve. We are going to be talking about looking at it in details. So these are some examples of the Hilbert curve. It takes of different orders. We have order 1, order 2, order 3. So one important parameter that is used when considering the Hilbert curve is the order of the curve. So to generate the curve, you give the order as an input. So an order, we can see on our screen, we can see the different curves generated for the different orders that have been given. The higher the order, the more dense is the curve. So we are going to the first part of our objective was to look at the literature to understand the state of the art work in the domain of image-based Android malware detection. We carried out a comprehensive systematic literature of more than 100 existing approaches that use the image-based techniques with machine learning and deep learning for Android malware detection. This enables us to understand where the current state of the research in this domain and the gaps for future research. So the objective of the literature review was to identify and to summarize and evaluate the current theory and methods on image-based Android malware detection, propose a comprehensive taxonomy to classify the state-of-the-art research in this area, and to identify methodological problems and gaps. So in carrying out this literature review, we adopted the systematic literature review approach by Rodrigo and all. We also took into account the lessons from Kishenham and all. We also made use of the PRISMA, preferred reporting items, systematic literature review checklist, and flow diagram to improve the transparency and quality of the review. The steps we followed in the review was to define the main research questions, we define keywords, we define search strings, we define search engines, we did some string refinements, and finally, we had our final search screens, which we ran on different search engines to retrieve our papers. We downloaded and stored the search results. We defined an inclusion and exclusion criteria. We selected papers first by looking at their title and abstract. At the second level, we looked at the introduction and conclusion. And finally, at the third stage, we did a complete and a thorough reading of the paper using a quality checklist. Then we then went further to extract the relevant answers to the research questions we earlier posed. So we also used the peacock method to define our research questions. It's a popular method that is often being used for systematic literature reviews. So applying the peacock method to define our research questions gave us this. We identified the population, which our population was the Android operating system. We have the how, what we are looking for. We are looking for papers that are in the image processing domain. We did not really do some comparisons. We want to categorize, our aim was to categorize and classify these image processing methods, and in the context of Android security, malware detection. So the first research question we were trying to answer was, how can existing research on image-based methods for Android malware detection be classified? This was the first question we are trying to answer in our literature review. Our second research question was, what approaches have been developed for image-based Android malware detection? We needed to understand the different approaches that has been developed. And to do that, we had sub-questions like what Android features are used for image-based generation. As we saw earlier, an Android app has several components that can be used for malware detection. Those components that have been used for image generation. We also needed to understand how these features were converted into images. Then we also wanted to understand what types of images were generated from this component. There are different types of digital images that can be generated. We have grayscale, we have color image that could also be generated. Then we also wanted to understand the image features that are used for model training. And further, we wanted to understand the machine and deep learning architectures that are used and the evaluation metrics used to evaluate the accuracy of the machine learning and deep learning models. Our final research question was to look at the patterns, gaps, and challenges that could be drawn from the current research efforts that will inform future research. So we'll not go into the details of the literature review because it's not our main topic for discussion here. We're going to skip that section, and we're going to be looking at specific objective 2, which is our bone of contention for this evening. And the task of the project was to propose an approach that uses the Hilbert space filling curve to characterize the behavior of Android applications by mapping the Android bytecodes to two-dimensional grayscale images while maintaining the spatial locality. So on our screen, we are trying to explain, to have a picture of our approach. We know that Android applications are normally stored, the executables are normally stored as sequence of bytes. And our intention is to transform those sequences that can be seen as a one-dimensional array into an image, which is a two-dimensional structure. So the Hilbert approach that we are going to be talking about helps us to efficiently transform data that is in one-dimensional or that is in form of an array into a 2D image structure. What we are gaining by using the Hilbert approach is that the spatial locality of data is maintained, meaning that two data items that are close together in the one-dimensional array will also be stored close together in the 2D array. This will help to minimize the problem we identified, the initial problem of distortion, where we will have two data items close together, or two instructions, let me put it that way, two instructions that are close together in the Android app, and during the conversion process, those two instructions will be found very far apart or distorted. With the Hilbert approach, it ensures that two data items that are close together will also be close together in the final image that is generated. So we say that the Hilbert space filling curve maintains the spatial locality of the Android app. It tries to maintain the structure of the executable file that we are going to be transforming as an image. So on the screen, we have the algorithm that translates the Hilbert curve node into Cartesian. It's actually a mapping, living from 1D. Look at what we have here. We are living from something that is linear to a two-dimensional structure. It means we'll be transforming indexes that are on an array to coordinates. So what our Hilbert algorithm does is to calculate these x and y coordinates that corresponds to an index in that array. So this is what the algorithm does. Then the main steps of our approach, we have three main steps. The first step was to collect the apps, our data set, carry out some pre-processing. And the pre-processing step consisted of extracting the DEX file. We said the Android APK file has several components, and we decided to use the DEX component because that is where Android stores the application logic of the file. To understand the behavior of an Android app, it's better to look at the DEX file. So our first step is to extract that DEX file from the APK file. Then we went further to extract the data section. The data section is actually where the code of the Android application is located. There are some works that are using the entire DEX, but as we saw earlier, the DEX files have several other subsections which may provide noise, which may be noisy if those sections are used for detection. So we extract just the data section that contains the actual code. Then the next major step in our approach is to generate, of course, the image from the extracted DEX data section file. And the images are generated using the Hilbert space filling curves, which maps an array or a byte sequence that is from 1D to an image which is a 2D data structure. So at the end of the day, we have a data set of images of benign and malicious apps. This data set now is given to our third, is used in our third step, which consists of detecting or classifying the apps as malicious or benign. Here we feed the images into a deep learning model, which is going to take care of classifying the images as malware and benign. So those are the three main steps of our approach. As we said, a DEX file has several sections. We are interested in the data section. So we extracted the data section in order to reduce noise from the file. And also, when we extract the data section is smaller than the entire text file. We also gain in resources, the cost of memory and processing time. So this is on the screen. We have our Hilbert image generation approach, which maps the DEX data section file that is extracted into an image. So the detection architecture consists of feeding the images into the models and our AI models. We use deep learning convolutional neural network models. We created a custom convolutional neural network. We also made use of some existing excellent image classification models that already exist, which we call pre-trained models. These pre-trained models are capable of extracting features from the images, from the input images, and that can be used to distinguish apps. So the 4 pre-trained AI models that we use are VGG16. We also use Inception V3. We also use ResNet 50 and EfficientNet B0. All these models are state-of-the-art image classification models. These are models that have proven their worth. They have won several image classification challenges. We make use of these models in this task. For the classification output, we use a sigmoid classification function, in order to provide for non-linearity. Then at the end, we evaluated our model based on accuracy. The following matrices: we had accuracy, precision, recall, and F1 score. We also calculated the AUC score. These are some of the matrices that we use to evaluate our final model. So as a result, we started with a data set that consisted of 9,100 benign apps and 8,700 malicious apps. Due to resource constraints, we randomly selected 5,000 benign and 5,000 malicious apps from the data set. The data set that we used was the Android Zoo data set, which has more than 22 million apps. During the extraction process, we noticed that there are some Android apps with multiple text files. Others have single text files. So the single text apps were 4,969 for the benign sample and 4,560. While the multi-text files for the benign were 30, and for the malicious sample were 435. That gave us a total final data set of 4,999 benign and 4,995 malicious samples. We have the discrepancy because we noticed that some of the apps had problems during the extraction process. They failed during the extraction process. That's why we are leaving from 5,000 to 4,999. Then after image generation, we successfully generated 4,995 benign and 4,995 malicious apps. So we had three data sets that were generated for our experiments. The first data set, of course, was generated using the proposed Hilbert approach, which we use to generate images from the text data section. Then we also generated images from the entire text file. That gave us a second data set. Then we use, we wanted to compare our approach with a state-of-art approach. This state-of-art approach is called the text-ray approach. We also generated images following the approach in order to enable us compare our approach to a state-of-art approach. So we had those three sets of data sets that were generated. For model training and testing, we use the tenfold cross-validation to evaluate the model performance, where 90% of the data was used for training, 5% for validation, and 5% for final testing. We also use early stopping in order to prevent our model from overfitting.
Hi, Benedict. I don't want to interrupt you, but we have a question in the chat from Idris Tafo.
Yeah.
And I think it's 2 slides back. That's why it's from 2 slides back.
Okay.
It's asking, please, data is an image or a text file?
Data is an image or a text file? Is that the question? Can I get the question well?
Yeah. So what is the structure of the data? Are you working with an image or a text file?
No, we are working with our data. Final data set consists of images, not text files. Please, we have images, not text files. Remember that from our approach, we start with the APK files, which are actually Android application files. Then we extract certain properties from those files, which we transform into images. So our final data set consists of images and not text files.
Perfect.
I don't know if I've answered the question.
I guess so. Idris will tell us in the chat. You can continue. Thank you.
Oh, okay. So we had three questions which we wanted to answer in our results section. The first question was, how efficient is our approach, the Hilbert curve approach, as a means of representing Android application binaries? Then the second research question, which we were looking forward to answer, was how effective is our approach compared to other state-of-the-art approaches? Then the last research questions was, what is the impact of using only the data section of the text file as opposed to using the entire text file to perform? So we had other questions like, what is the impact of the byte sequence distortion? We had to, since we are talking about distortion, we had to measure that, the impact of that distortion. Then as the fifth question, research question, which we attempted to answer, was, what is the impact of the dataset imbalance on the performance of our approach? And the last but not the least was, what is the impact of image resizing on the performance of our approach? So for research question 1, we noticed that the Inception V3 model achieves the highest accuracy of 97.99%, precision of 98.50, recall of 97.50, and an F1 score of 97.99. We can look at the plots, the bar charts show that the Inception V3 has the highest bars for accuracy, precision, recall, and F1 score. The next research question was to see how effective our approach compared to the state-of-art approaches. We compared our approach with the text-ray approach, which is also another image generation approach, another method of detecting malware that is based on images, which is explained in the literature review section of our work. We noticed that our approach performed better than the text-ray approach. in all the matrices, accuracy, precision, and recall. We had a larger data set as compared to what was used by Dexray. So the next research question was to look at the impact of using only the data section of the DEX file as opposed to using the entire DEX file on the performance of our approach. We should notice that a DEX file has different sections. We extracted the section that has only the code, and that's what we use in our experiment. So we wanted to compare it with using the entire DEX file as used in so many approaches in the literature. And we noticed that the bars in blues represent the DEX data section, the results obtained with the DEX data section, while the bars in orange represent the results with the entire DEX file. We can see that with all the evaluation matrices, we have the bars in blues are higher, representing the fact that we have a better performance with using the DEX data section, which is a smaller file, which is a subset of the DEX file. This is quite advantageous because it avoids us having losing in performance in terms of memory and computational speed. So we also measured the impact of the byte sequence distortion by comparing the images generated using the Hilbert approach and that generated using the traditional approach of the literature to see from if we look at the comparison, we'll notice that the results from using the Hilbert approach is better in all aspects than that generated using the traditional approach. For the four models, for the four deep learning models, our Hilbert approach performs better than the traditional approach for generating images. So we had some limitations. We noticed that using the Hilbert approach, there is a lot of padding. We need to, since we have to generate rectangular images, at times the file sizes are smaller. We need to pad them. So the image Hilbert approach requires a lot of padding as compared to the traditional approach. Then we also have issues with resizing the images, which we think is something that has to be handled in future. So these are the main limitations of our approach. To conclude, we'll say that this work presents a twofold contributions to the field of image-based Android malware detection. Firstly, it provides a comprehensive systematic literature review of the current state-of-the-art research in this domain. And secondly, the study proposes a novel method that uses the Hilbert space filling curve to represent app bytecode as two-dimensional images. The approach aims to preserve the inherent spatial relationships within the bytecode, addressing the limitation of prior work that neglected the byte sequence structure when converting binaries to rectangular images. The experiments were conducted on a dataset of 9,990 apps. It shows that the Hilbert imaging technique with deep learning performs better than the traditional approach. And we saw that amongst the models, the AI models that we used, the 4 AI models that we used in the Inception V3 model, achieved the highest score highest accuracy of 97.89%. We can say that the findings from this work demonstrate the use of the Hilbert space filling curve visualization combined with advanced deep learning classifiers and presents an effective solution for accurate Android malware detection. So thank you for your keen attention, and I'm open for any questions, for your questions.
Thank you very much for your insightful presentation. We can already take questions from the chat from Idris. And please, for the others who are listening to the presentation, you do not hesitate to please send in your questions for Benedict. So we have a question from Idris again. He says, please understand the postulate to use the images to enter. The DEX format is correctly formatted. String, table, class, list, field, table. So the intuitive way and approach with the LLM would have been ideal. So his question is in two parts.
Okay. Yeah.
I don't know if you can read
remember
it from
I
the
said,
chat.
yeah. Are you done? Are you done? The questions?
So the question is in two parts. The first part says, please understand the postulate to use images, to use the images to enter. The DEX format is correctly formatted: string, table, class, list, field, table. And then he says, so the intuitive way, I guess he means approach with the LLM would have been ideal. Please really understand the basic postulate. So I'm not sure if I'm getting this right, but I think what he's saying is that if you take the original formatting of the DEX, so the DEX file or the original DEX format, so it could be in the form string, table, class, list, field, which can then be used by a large language model. So maybe he thinks that you could have used this as text and not images. Do you have a comment on that?
Yeah, of course. I think he's on point. I think at one point it's important to explore looking at the text file as a text, and using models, AI models that are good in text to look at the performance. But I was also trying to explore what the image models can produce. The approach is image based. We were trying also to take advantage of the powerful image AI models that exist, make use of them. So in order to do that, we needed to transform our DEX file into an image. So I think it will be very important for us to explore the text models to see what results we can have. But that does not include our own approach. I don't know if Prof has something to say.
Yes, can I say something?
Yes, of course, Prof, you can.
Yeah, one of the motivations that we had is to deal with the obfuscated technique that attackers using nowadays. You know, because they can take an app and put something inside. You know, to lure the users, the final users. You know, and now what we had to do is to find a way to restructure, to find a stable structure that can reliably tell us that something is going wrong. Okay, that's why we rely on this image structure, to see whether someone takes the original apps and put something inside, let's say a bad script inside, and to try to see, okay, with our approach, we can look at it and see something that is suspecting. Okay, this is what I can say. Yeah.
Yeah, but then to follow up on Idris, we can do the same, treating the source code, so the malware files, as sequences, byte sequences. We can treat them as text, or
it's also possible, but if can
yes,
I move on?
yes.
Yeah, it's also it's possible, to look at the text, because the APK is a structure, is a dynamic structure which involves a lot of parts. Some of the parts also include text, like if we take the manifest of the app, of the APK, we have a lot of text inside. But now we're taking the text file, which which is closer to the devices, right? So it means it includes normally the 0 and 1, something like, and closer to the device. So what we had to do is now to take the structure of this numerical information, to try to see what we can do with these mathematical theories.
Okay. I don't know if it is clearer for Idris. You can let us know in the comment section, or you can add a follow-up question. I am not sure, maybe I missed it. I didn't see the slide of the effect of class imbalance on the
the exercise, I think we didn't include it, but it's found in the original paper.
original paper.
To limit
Okay.
since we are looking at time, so we didn't include all all these questions are answered in the original paper.
Yeah,
Yeah,
I was
but
asking
you
because
can say something, Ben. You can say
Okay.
something, right?
Yeah, I can say something about it. Yeah, so we investigated our approach to see the effect of class imbalance, because it's important to consider class imbalance, because normally in the wild we have more benign samples than malicious samples. So it means that the models that will be created, we will create, will naturally see more benign samples than malicious
that's
samples. We notice.
exactly why I was asking the question, because I
Mhm.
thought that in a real life situation, the malware cases will be really the minority.
Yes, with the minority, yeah, yeah. So the impact of that data imbalance on the performance of the proposed approach was thoroughly examined. We considered data sets with ratios of malware and benign samples ranging from 1 to 1 to 1 to 8, meaning one malware to 1 50-50, and one malware to 8 benigns. So that's what we did. We tried to take these ratios, and we noticed that there was some dip in performance. So despite the trade-off, the 1 to 8 imbalance ratio achieved a precision. We had a high precision, but there was a drop in recall, and of course the F1 score. And that demonstrated that the proposed approach still remains viable and effective in a practical deployment scenarios with realistic class imbalances. So I think that was tested, as I said. The precision was very high, but we had a slight drop in the recall rate.
What was the precision percentage, please?
The precision was 99.99%.
And the recall?
The recall was 79.94%,
Okay.
giving an F1 score of 90%.
Okay.
I think that can be accepted practically.
Yeah, of course. I have a Okay, so there is another question from Idris. Maybe I will take that first. In the comment section, he's asking, the binary of the application must be very, very complicated to be entirely captured with an image. So maybe Idris is still insisting that the image modeling for him seems a bit, maybe not the most straightforward approach for this.
No, I think when you have a sequence of bytes that are represented in memory, when we are looking at the sequence of bytes or maybe the machine language in the memory of a computer, you can interpret it as anything. You can interpret it as an image, you can interpret it as text. It depends on what you want to do with it. I don't think it's something that is complicated. It's just due to, it depends on what you want to do with it. Also, we wanted to take advantage of AI models that are good in image classification. So we are looking at that sequence, that binary sequence, that executable code of the app as an image. And that is why we have proposed that this our Hilbert transform mapping to map that byte sequence to an image. It's a binary sequence in memory, can be interpreted, can be taken for anything. It can be interpreted as a text, it can be interpreted as an image, it can be interpreted as a number. It depends on what we want to do with it.
Okay.
Yeah.
So what we can, I can add something.
Yeah.
Yeah, in fact, it's a world project, you know, and there's some members of my research group who are working on these text, ways of structuring the binary. Okay, so Benedict is working on the image landscape, so it means that is looking at how to take this binary to look into and find a way to have a stable structure that can be used by intelligence, you know. But here the question is not to, you know, to find the best structure, either textual or image, but how, when we're using how to assist these deep learning techniques, you know, to reflect in a reliable way, you know, the knowledge that can be used to detect suspected behavior. Okay, there are other people that will be presented maybe later or in the future day, based on that use textual information, the binary APK, to recognize this bad behavior. Thanks.
Perfect. Okay, before we take a question from Honoré, I just want to ask, maybe I should have asked that before. So what kind of malwares are we talking about concretely? Because I was a bit wondering first, so yeah, are you looking at a specific kind of malware that can get into any Android app? And how does your model then behaves if we have different types of malwares? Yeah. I see that we lost Ben.
Yes, what I can reply to you is what we use is you know, we taking general aspect of malware. We didn't take specific kind of. Okay. This is the first step. Now the second step that we move forward is now to try to determine families of
malwares.
What the first thing was that to investigate if it's feasible to use this mathematical theory, if it's feasible to use these mathematical theories to have acceptable result. The next step now is, okay, now we look into to see whether now we can characterize families of you know, and if this
Malwares.
model can remain, you know, robust. Yeah.
Okay.
This is a
So
good question. Thank you.
the data you use, it's some publicly available data that has already been labeled, and so
Yeah.
the type of the malware itself, like you don't know exactly what type of malware it is, or do you know
Yeah.
what it is?
Yes.
Okay.
You're right. For now, we do use existing data set with different behaviors of malware, of Android malware. Yeah. Now that we saw that these stories, you know, gave some interesting result. Now we move forward to say, okay, from this data set, we try to group or to find families from, you know, to try to see whether the model remains robust.
Okay. We have a question from Honoré Wete who says, you worked at the bits level and dealt with deformation. What difference do you make with the Hamming distance used to differentiate bit sequences? I did miss some parts, so please forgive me. You are forgiven, Honoré.
Okay, this is a great question. And you did see as one of our perspectives to look into the padding issues. Okay, this is one of the perspective, and this perspective is closely related to this question, I mean distance. So we look into two aspects now. This distance, let's say this paging issue, and then we look also into the dimensions of the image. You see, so during the first investigation, we can say that we set the dimension of the images. But now moving forward, we need to look to find a relation somehow between the dimension and also the locality of information within the images. So this question remains. We look into this in the perspective.
Okay. Maybe can I follow up on this question because you mentioned the padding issue. I just
Yeah.
need to understand
Mm-hmm.
because the padding, what I know about padding is that usually when you are working with sequences of information or yeah like informations in matrices, then you might want to complete for missing out information with some value for padding just to ensure consistency in your dimensions. Is that the padding you're talking about?
Yes.
Okay, so doing some kind of zero padding to ensure that you can confidently
Yes.
ensure your dimensions while going across with your
Yes.
convolutions. But how did
Yes.
that
Yes.
then affect your modeling? Because you said that there was an effect of too much padding. Do you mean in terms of resources or even on the performance of the model?
Guys, in terms of losses of information.
How? I'm struggling to understand that.
Yeah, I think we investigate or we experimented. We experimented also these effects on our data set, and we
Okay.
obtained some result that we try to discuss to have this perspective. I don't know if Ben will have shown this.
Yeah, I had some issues with network, so I didn't get the question to the end. But I can confirm with what she's saying is correct. Since we are generating rectangular images, we can have apps of different sizes, and to make the apps fit our square images that we generate, that we want to
Yeah.
generate, we will need to pad to make it to make it up to the size. We noticed that with our approach, since we are generating square images, we may require a lot of padding.
Okay.
Yes. and that can, add some noise to the data. We are only thinking about uh, trying to see how we can solve these padding issues in the future work.
Okay. Okay, I see. Because, for example, in sequential information, by sequential I mean time
Mhm,
series or in natural language
mhm,
processing.
mhm,
What usually
mhm,
happens and what has already been integrated with models like
mhm,
the long short-term memory, so the recurrent neural models from either TensorFlow or
mhm,
PyTorch, is that you will pad these sequences so that you can have
mhm.
the exact same size of information within your tensor. So it's the same idea. Let's say you are modeling
Yes.
sentences. You are modeling sentences, but the first instance has a sentence of 10 words. The second instance has a sentence with 50 words. So because you want all of those to be in the same batch, you will have to pad the first sequence up to the greatest length. So what has been integrated here is that you will pad with some number, but you actually introduce a mask that keeps track of where the padding was done. And so at the point of backpropagating, the weights attached to these padded words are not considered.
Wow. Okay. Wow. That's
So
interesting. That's interesting. So that's you are only giving us one way of dealing
yeah,
with padding, with those padding
yeah,
bits.
I'm not
I
so
think
versed
it's really interesting.
with
Yeah.
image data, so I don't know exactly how that happens there. But I
The padding is
understand
done.
you.
Yeah.
No, no, I mean I don't know how the padding is taken into account at the time of backpropagating the
Mhm.
loss. Because you do not want
Okay.
the problem is that you do not want the information from these padded entries to be backpropagated
Yeah.
onto the other
Yes,
the
yes, that's the main
Exactly.
issue. Yeah,
yeah,
that's the main constraint.
Yeah.
yeah. So that's what they
I
have
think that is.
introduced in the
I
sequential
think. I
model.
think that. I think it's a solution you're giving. You are giving us, and we are going to investigate that.
Okay.
With as we said, with these image models, you have to decide. You have to give a fixed width and a fixed height, and you may have uh, apps or data that is maybe less than the size or more than the size. When it's less
Yeah.
than the size, you have to complete with some padding bits. When it's bigger than the size, you have to resize.
Yeah.
Fortunately for us, I didn't mention resizing too is very problematic because you can crop off areas in your original data that
Yeah.
can be valuable for the detection process if it's not carefully done. In our
Okay.
approach, we did not just resize anyhow. We use the interpolation technique to take care of resizing. So I think that's one of the things that we did. But I think that the resizing issue still needs,
Yeah.
proper investigation.
Okay. Good.
To
We have
look at the
another
best,
question.
because several techniques, when we look at works that have been done, we notice that there are a lot of work, several techniques that have been, used to resize or compress images. It will be interesting for us to know which technique is the best under what conditions.
Okay. We have another question from Idris. So questions are coming. Due to my experience, the unbalanced data is easy to find a solution, cross-validation. Please, I would like to know how the distortion of the sequence of
Let
bytes
me
affects the
see.
results.
Let's see. Please,
I don't know if the question is clear or
solution. Yeah, yeah. As earlier said, we investigated different ratios, different imbalance ratios in our experiment, taking maybe 1-to-1. We started with a 1-to-1, 50-50, maybe that is a balanced data. Then we also ran experiments with other ratios like 1-to-2, that is taking for every malicious app, we are considered 2 benign apps. If we have 50 malicious apps, we take 100 benign apps. We went up to a ratio of 1:8, which is what is normally required for a real life scenario. If the 1:8 ratio is good, then I think that's you can conclude that if the model still performs up to that level, you can conclude that the model is good and can be deployed in a real life scenario. And that's the result I gave you of late, that using a 1:8 ratio, we noticed that the precision was very high, while the recall was a bit lower. That gave us an F1 score of 90%. So I don't know if I'm answering his question.
Yeah, I
Or he's
think he
answering
doesn't.
is it due
Yeah,
to his experience. Mm-hmm.
I think he doesn't
Yeah.
have issues with cross validation. He thinks that with unbalanced data. He thinks that cross validation can help solve issues of unbalanced data.
Mm-hmm.
But his real question is, he wants to know how the distortion of the
Mm-hmm.
sequence of bytes affects the results.
Yeah, that's we ran our first one of our research questions was to investigate the effect of this distortion, where we considered what generating images using the normal approach, the normal traditional approach, and generating images using our proposed approach, which minimizes this distortion effect. And we noticed that our proposed approach had better results in terms of all the matrices that were used, all the performance matrices that were used. From there, we can conclude that our approach, minimizes this distortion effect. Remember that there are two. We started with the premise that what the traditional approaches that are used to generate images, they don't consider the structure of the original structure of the byte sequence. They don't consider the fact that what there's when you look at the code, the executable code of a file, there's a certain order. Instruction 1 comes after instruction 2. Normally, the executable file of an app can best be captured in a sequential order. You can you can put the instructions, you can number the instructions from 1 to a certain n, which will give you some form of an array data structure. And what the image-based approaches are doing is taking that structure and mapping to something two-dimensional. So we are thinking that instead of just doing it anyhow can lead to distortion. Using our Hilbert approach will help minimize that distortion, because the Hilbert approach looks at the spatial locality, tries to minimize the spatial locality, ensuring that if there are two instructions that are closer together in your executable in their original file, they'll also be closer together in the image. So we did that, and we had higher results in terms of all the performance as compared to the other images that did not take care of the distortion. So I think that with that result we can conclude that our approach minimized this distortion effect. I don't know if there's a follow-up question I would like to take. I don't know if he has understood me.
Okay. Yeah, Idris,
I don't know.
just
I don't
keep
know if
on.
Prof has what to say. Has something to add. Maybe Prof has something to add.
No, that's fine. That's fine. Huh?
Yeah, because I mean, if you did your image modeling with and without taking into account compensating for any distortion, then you might want to conclude that using the Hilbert spaces actually reduces some information loss via distortion of your sequence. So we have another question from Honoré. For the generation, are you using diffusion models?
Diffusion? No, we didn't. For the generation of
images, I think. But
no, we didn't use diffusion models, huh?
maybe you
is
can
it
just refresh for him how you generate your images. Or maybe he didn't understand what you meant by image generation.
No, maybe I think what I see in this question is that I see it as a proposal, maybe that we can keep with us. And now what we did is that before giving to CNN or to deep learning models, I would say like that, we're trying to pre-process information or data that we had, APK transformed, and we put inside the Hilbert curve model to try to set this stable structure from the original one before giving to. So the transformation or the generation, comes from applying the Hilbert curve transformation to have now the transform images, I would say like that, to give to the deep learning models.
Okay. We have another question from Honoré that says, please, you are padding your data and simultaneously you are generating. How both fit in your pipeline? Okay.
You are padding data and simultaneously.
Well, I think it's... Sorry?
Yes, can you?
Yeah, I wanted to say that I think it follows from the discussion we had before. I think if I understood correctly, they are not done simultaneously. So it's first leaving from your 1D array of byte sequences to 2D array matrices. Those are the images via the Hilbert curves. And then when you are modeling, let me just add Benedict to the scene. Yeah. So then when you are modeling the images with deep learning, you then have to do some padding.
Yes.
You are sliding when you are doing your convolutions over the matrix of images. You then have to
Yes.
So they are not really done simultaneously. One of them is like Benedict said, is a pre-processing step. So moving from the 1D array to the 2D images, and the other one, padding, happens during the modeling.
Yes.
Yeah, you're correct.
Oh, Idris is saying another question. I'm sorry. You don't need to be sorry. Just send the question. I think they are here for that.
We are there for that. We are there for that.
When you accept to present your work or to release your work to the public, you just have to bear
Yes, of course.
Getting the questions.
Yeah. It means that it's interesting,
Exactly. So the question here says, how did you characterize a different family of malware, knowing that they will have several different signatures according to the influence of other apps present on the mobile terminal?
Oh, yes. I think we discussed it before, right? So I said that this is the next step of our study. It's the next step of our study, in which we will now we now take families of malware to see whether the model remains robust. That's the next step of our project.
Family classification.
Yes. It's a great point that Igris mentioned. We are going step by step.
So we're not doing family. We didn't do family classification.
Yes.
Okay. We have
The
another
first thing
question.
we wanted to see if it's feasible. It should have been feasible to use these mathematical theories.
Yeah. We have another question from Honore that says, "Thank you for the explanation." Okay, I think he meant the explanation about the data padding and conversion from 1D to 2D. Thank you for the explanation. My point was about the steps until the final output. Okay, maybe I think Ben's screen is frozen again. Because maybe you might want to share the slide where you have the whole pipeline, so that he can see from
Yeah,
pre-processing to
Okay.
yeah.
Okay. I have try sharing my screen.
Yeah, just let me know when that's done so I can add it here.
Okay. Yeah, it's done. It's done.
Okay, thank you.
It's
It's coming.
done.
It's coming. Yeah, it's coming. It's loading.
Can you see my screen?
It's still loading on
it's
my.
loading. It's loading. It's coming, Ben.
Perfect.
Yeah, let me put full screen. Let me put the full screen option.
Yeah, perfect. I think Honore can see
Is
the.
it better this way? Yeah.
Yeah,
Yeah.
I think Honore can see the whole modeling overview. Yeah. So we have the APK archives, extraction of the DEX files, and then extraction of the data section from the DEX file. He showed that using the entire DEX file doesn't help. On the contrary, it reduces performance. And then convert the data section file to image. So that's what he calls image generation via the Hilbert curves. And then he has his grayscale images. Okay, which then goes to the so he splits that into training and testing, and then it goes to his CNN model, and he attaches a sigmoid function for prediction. He says thank you. Honore says thank you for the pipeline. Thank you. Okay, but Honore has another question. How are the malware represented? What is the data structure?
Oh yeah.
The
Did
data
you present
structure.
the structure, Ben, of
The structure of
yeah, the whole APK, right?
yeah, I
The
did. I did.
components.
Maybe I should go back to it. The structure of the APK is in the background section or something like that. Yeah. So this actually the APK structure. We highlighted the main components, which are the manifest file, the libraries, the resource files, and the DEX file. And we said we are going to be focused on the DEX file because that is where the executable code component is found. So we are extracting the DEX files from both benign apps and the and malicious apps. all apps, all Android apps have this. They have this. They have a manifest. They have a library. They have resource. They have a text file. So you are working with the text files of benign and malicious apps. I don't know if I've answered the question.
I don't know
But
how
I
Malware
think
represent.
it's asking for data structure. So when you transform the original data, let's take the text files, what do you have? What the matrices that you have after and so on? What's the, yeah, can you show the data structure?
Yeah, I think it's
Okay,
I think
yeah,
it's a
it's just a
slide before
stream
this
of
one.
which one? This one? This one?
No, no. There is a slide where you show the sequence, the vector. Yeah, this one.
Yes,
Or
this one. No,
Yeah,
back.
this one. Yeah, yeah.
No,
no.
Back.
no, the other one with vector and matrices.
Yes,
Yeah, this one.
Yeah.
research
So I was
design.
trying to say that. Yeah, I was trying to say that. Yes, I was trying to say that we looked at our DEX file as a sequence of as an array, a one dimensional array, where these values represents the the byte codes in binary values. V0 is a binary value, V1 is a binary value. We actually, I want to come to this image. We This one is clearer because we were taking the sequence of 8 bits. Then we looked at the corresponding decimal value to have the grayscale image. So we took sequences of 8 bits, which we converted to decimal, that gave us the intensity or the value of maybe at that point. That's what we did. You know, the executable file is a binary file, so it's possible to read it in groups of eight, which we
Okay.
use as the pixel values at a particular point. So a pixel value at a particular point in an image of the image corresponds to a 1 byte of information from the text file. That's what gives the intensity of the different intensities of the pixel values. So since we are taking 8 bits, it means that we are going to be having values. The intensity is going to be ranging from 0 to 255. I hope I don't know if it's understood.
I think so because
Hello.
Honoré said thank you.
Okay, okay.
We have another question from Idris. Please, is it possible to share the architecture of the model again? Okay, no, it's fine. I think he saw it. Yeah. I have a problem with flattening. How do you mean, Idris? Please explain it. I have the problem with flattening. Please, Idris, explain a bit more the question. So we can take the next question from Honoré. Have you thought about transforming the bytes into a dynamic graph?
Come again, please. Come again. I didn't get you well.
Have you thought about transforming the bytes into a dynamic graph instead of
Into
an image? A dynamic graph.
graph. Oh, wow. Okay. Yeah, that is something we want to explore too.
Yeah, thanks for this question. We will keep it to explore it later. That's great.
Okay. Maybe I have a question. In your results, you show that the V3, the Inception V3 had the best performance. I was wondering, do you have any idea why V3 had the best performance? Like, what is your
I think that's
intuition?
yeah, yeah. I to be honest, it really it will require that we get into the architecture to understand the architecture of it. I have the impression that because since the images tries to capture the input images tries to capture the spatial structure of the app, I feel that the the arrangements of the way the convolutional layers are arranged in Inception V3 favors this type of input. That's just the best explanation I could give.
Okay. I'm asking the
Because
question because
all of yes, all of those architectures are made up of at the base we have convolutional neural networks and pooling layers arranged in in different orders and all those type of things.
yeah.
So yeah, it's the question is pertinent. The question is pertinent.
But for on all of those models you used, do you just use the architecture, or you import pre-trained weights from those models?
I imported pre-trained weights. Yes, from
Okay,
those models, I imported pre-trained weights. I
that's
only
very
removed the last layer where
yeah.
I had to do a classification, a binary
Mm-hmm,
classification.
mm-hmm.
So yes, I pre-trained weights were imported,
Yeah, that's why I'm
and
asking because I know that all those models
the
were
the, the only layer I had to do my binary classification.
okay. Yeah, so my question was with regards to
Hello,
that because
can you get
those
me?
models have been trained. Uh,
Hello,
Maybe Benedict's network is disturbing. Benedict, can you hear me?
I have issues with network.
Yeah, I think there is some
Yeah, I have
delay.
issues. Yeah,
But is it better now or
yes,
not?
better. It's better now. You can go on, please.
Okay. I was saying that I was asking the question because those models normally have been they were all built and used on the ImageNet dataset,
Yeah,
if I
ImageNet
recall correct.
dataset. Yes,
Yes, for
exactly.
predicting
Yeah,
the
exactly.
1,000 classes. And
Mm-hmm.
so I know that so they were kind of built one after the other by researchers who wanted to then like beat the state of the art
Yes, be the state of the art of the ImageNet
of the
challenge.
preceding model. So, and I
Mm-hmm.
think
Mm-hmm.
amongst the ones you presented, but maybe I'm having it wrong. I thought EfficientNet was the one that had the best performance because after EfficientNet, we then had the Vision Transformer. So
Mm-hmm.
I thought maybe EfficientNet B0 will perform best. But yeah,
Mm-hmm.
maybe I still have to check. I still have to check if Inception V3 has
Mm-hmm.
reported a better performance than EfficientNet on the ImageNet dataset. I was just wondering, like, why would this be? Because when you showed the model, I thought, if EfficientNet is the one that reported the best performance on the on the ImageNet dataset, then maybe it's the one with like the best initial weights to start with, and but yeah, maybe not.
Yeah, it's not automatic.
Yeah,
It's
Yeah,
not, yeah, it's not depend really on the structure of the data
yeah,
that you have. It's
yeah,
very
yes.
versatile. It's very, yeah, and yeah, we need to look into maybe to explain, but it's not, we cannot take it from what has been done with ImageNet to, to transfer directly into our data, you see.
yeah.
Yeah, this is what I can add.
And did you also try like
Prof,
a
Prof,
simple?
can I say something with respect to that?
Yeah,
Can I
yes,
say
of
something
course,
with
of
respect to
course,
that?
of course. Mm.
So I think it's we have, so far as these models cannot be explained. There's this pertinent issue of explainability of deep learning models. So far as these models cannot be explained, they will obviously behave differently if presented different data sets with different distributions. I want to say that the fact that for example, efficient net came after maybe inception does not mean that efficient net would perform better than uh, inception on all data distributions. That comparison was done using a particular data distribution. But is it the same for all data distribution? I don't think so. I don't know if you can get my point.
Yeah.
Yes,
I
I
think
think you're right. I think she was, she was just trying
Mhm.
to ask herself
To
whether
understand.
is it a
yeah.
connection or something
Mhm.
like. It's a great question
Mhm.
also. Yeah.
But
I think I thought
actually,
about,
you just
yeah.
said something
Mhm.
interesting, Benedict. You mentioned the
Mhm.
explainability aspect. Maybe if you go into each of the models and check like the most and check, uh, I don't know. You can use maybe the activation maps to look at regions of the
Mhm.
images that explain whether your instance is a malware or not. Maybe that can
Mhm.
give some intuition as to why Inception V3 is better than all the other models. Maybe it focuses on some parts of the images that the others do
Yeah.
not.
Yeah.
But that's
For this
even
particular distribution. Mhm.
why didn't you even do some explainability on the data?
Yeah. Yeah.
I mean, you cannot do everything. It's okay.
Yeah. Yeah. Yeah.
Yeah, I
It's
can recruit.
really,
Let me recruit you directly for that, my Jeff.
yeah. Mhm.
Are you
Sorry.
interested in that? Are you interested, Vanessa, in that?
In
In this
sorry.
explainability stuff. In this explainability stuff.
Well, I am because I am working on medical data, so I almost always
Okay.
have to do it. Yeah.
Okay. Okay, that's great. In fact, as I told you, it's a big project, We have also someone working on explainability, and other one on textual contents, and he's working on image.
Okay. Okay. I see.
Yeah.
Okay. We have a question by this that says maybe the image is not the good. It's not the good representation. Graph knowledge can be.
Yeah, it's possible. It's possible. We are taking consideration all these remarks. Thank you for that. It's possible that we need to look into graph knowledge. If you are interested, we can also work together, collaborate, to see whether we can have something better.
Um, are there any other questions? I don't see any new question from the chat. Oh, okay. One question just arrived from Honore. From my understanding, you take the byte sequences and build an image from it, then feed it to a CNN. You use Hilbert spaces. You use Hilbert space at the building stage. Yeah.
Exactly. Exactly. Exactly.
Mm. Oh yeah, I asked something. I asked a question, but yeah, maybe we didn't understand each other. So I was asking if you also tried like a simple CNN architecture instead of using the pre-trained like complex models.
Yeah, I did. I
Oh,
did.
okay,
I
okay,
did.
okay.
Yeah, I used a simple, the comparison I did with Dexray I used a simple CNN architecture. I think,
Okay.
let me, if I should share,
Okay.
that was done.
Perfect.
So what I can add is that we had a pre-work with another master student that showed that it's possible now to pre-process the images that we give to CNN. This was the preferred step, I would say, like that. So now that's why after we put now Ben to see concretely what we can do to help these existing deep learning models. So before it wasn't this Hilbert space stuff. It was something like SVT, to compress the image, to try to to compress these images in a robust way. And we had also interesting results that we understood that it's possible, to support these decision making, relying on these deep learning models. Thanks.
Okay. Okay. Maybe my final question is then about practicability. So I guess a way that your system will be used is that if someone sends me, so I have an Android phone, if someone sends me an app or if I download an app, then your system scans through this app to detect whether there is a
Yeah,
malware or not before I install it, right?
exactly. It can be used both with during, maybe prior to installation, and maybe since it's based on APK, we can also want to scan all the apps that are already on your phone to check if they are, they are malicious or not.
Okay.
Yeah.
Okay. Because my question was then, so yeah, so how do you see the practicality of using this concretely? So,
Yeah.
for example, imagine you could transform this into a system that goes into people's phone. How would this happen?
Yeah, I think that given the models that we've used, they are very, very,
Light?
I would say, performance intensive models that may not, uh, will not be best for small devices like the mobile phone. So if this approach was to be deployed, we may need to have maybe some form of cloud server, some that does some computing somewhere, and the results are sent back to the phone. So we need a cloud server where that does the actual uh, computing, and
Screening.
then the results are sent back to to the phone. Or there's another option: we could investigate the with other pre-trained models that could be installed directly on the phone. I'm thinking of mobile net, something like that,
Yeah.
to see the performance with mobile net. I think if we have to investigate that, we will have a solution that can be local. So there are two possibilities: either having a remote server that does the intensive computation and then send the results back to the phone, or we have a mobile. We go in for the mobile net architecture, investigate to see the performance. But I must say that generating the images using the Hilbert approach is something that also takes a lot of time. It takes some time to generate images using the Hilbert approach, which is something that we also need to investigate. Honestly, it doesn't take, it's not, it takes a lot of time when you want to generate those Hilbert images. I don't think that will be really practical for,
But then my question is, what is the how can I say it? So, on a practical point of view, what is the relevance of the project? I mean, I'm not disputing that this project is relevant. I just want to understand. So, on a practical point of view, how relevant can this project be exploited? I think Benedict's screen is frozen again.
Hello?
Yes.
So,
Yeah.
yes, what I can say is that we, you know, what is used now in the Android ecosystem now is that when you develop an app, you put there is a pre-screen, there's a pre-screen phase that is conducted, to try to see if the app is malicious or not by default, by Google. And this process, has been demonstrated as not so reliable. That's why for now what people are doing is they put their app into a system like Virus Total. It's a platform on the cloud, on the web, where you can just upload your app, and then back you have the result of the analysis. So this is the same scheme that we want to put in place. We want to develop such systems so that people can go there and make an analysis of their app before installing in their phone. It
Okay.
won't be in line. It will be hybrid. In line there will be a client. There will be a client, module that will communicate directly with the server side, so that the app will be bi-directional, and the user can take decision making based on what he or she has back to the server. So
Okay.
this aim is to assist the users with signs, with first signs of app that they want to install in their system.
Okay. Uh, Another question from Honore. What have you learned about malware?
What have you learned about malware? Wonderful. This is a wonderful question. Ben, do you have any idea what do you learn about malware, my dear? Tell me, Ben, please.
I will say that when I
I mean,
was
you did a systematic
yes,
literature review then.
when I
So,
was generating the images, when I was
Hmm.
generating images from malware. Can you get me well? Are you getting
Yes,
me?
yes,
yes.
yes,
Yeah, when I
yes.
was generating images from malware and benign apps, I could clearly see that there were some patterns. Looking at just the images generated from the malwares, some malwares, I could see a clear pattern in those images, and which were different from images that were generated from benign apps. And I feel that that is what it resembles what we do in medicines, where you take the image of, maybe you do a chest scan of somebody that is sick and a chest scan of somebody that is not sick, or maybe that has TB and somebody that does not have TB. From those images, doctors can look at it and say that, okay, this man has a problem, this man does not have a problem. So you could clearly already see that, visualize that from the images that were generated from the apps. So that if I want to say something, that's what I learned from malwares, that they have their images, have certain patterns that even with your eyes you can see when you visualize them in form of images. And that is why what it is these image methods have been used so often, because you can clearly, from an image, you can easily see patterns. You can pick out patterns that indicate the maliciousness of an application. I don't know if I've
Yeah. So what I can
attempted an answer to that
also,
question.
yes, thank you, Ben, for your reaction. So what I can say also is that this work confirms that this app that we install in our system, they can pass these antiviruses that we have. You clearly see that because this app, once they are obfuscated, they have from their inside bad scripts and so on. So these antivirus that you install in your system, they are not reliable, in fact. So we need these mechanisms that are able to see in the structures of this app whether the app is changing the structure or not based on what the malware attacker is putting inside. We need these mechanisms that are robust to identify such bad effects. You see, what the antivirus are doing is that they're relying on these signatures database, which are static. Okay, once the app are transformed by the attackers, the antivirus are not able to detect them. So we need this novel mechanism now to be faithful, on which we can be faithful, so that we can trust very easily, based on what we have identified inside their structure. This is very important. That's why this project falls within this objective, to build such systems that people can trust. Is very important. So this was the first step, okay, that shows us it's feasible. It's very feasible. Now, normally we need to change the data set, or to take different behaviors of malware, of apps, to change the different behaviors, to see what we obtain as result, to see whether changing the structure can be detected by our model. So we learned a lot. I think we learned a lot from the perspective of, first of all, we need these mathematical theories. I can say that we need to rely on these mathematical theories, which have been proven by scientists. We need to use them to try to solve our issues. The second thing is that the different malware that we exploited, with time, if we have built some models based on some data set, we need the model to be timely robust, I will say like that. So the model that we build today, 2 years after or 5 years after, we won't be maybe effective. You see, this is also a question that we need to look at to look into very detailedly. This is what I can add. Hello, do you hear me?
Yes, I can.
Oh, that's perfect. That's perfect.
Okay. Actually, that's very interesting. Especially, then it makes sense from Benedict's reply that the performances were that high, because if with your mere eyes you can see that there is a pattern in the images in the images that differentiate a malware a benign from a benign app, then the models will be then good at identifying these discriminative features. But yeah, I was also curious to kind of know, like, the information he learned from the systematic literature review he conducted with regards to the malwares. But, hi,
With
Benedict.
regard to the, oh, can you
Yeah,
repeat it? It just came.
yeah. I was saying that since he did a systematic literature review regarding the malwares, like what were the key takeaways? I do not mean deep learning for malware detection. I just
Ah,
mean the
okay.
malwares themselves. What were the key takeaways?
Yeah, from literature review, from for systematic review.
Yeah. Like for example,
Then,
I wanted to know is this malware so is this like a big problem with the with Android apps, and maybe why Android operating system, do other operating systems have the same problem? These are the kind of information I was interested in. But yeah, I think he has network issues,
yes.
which
So what he did is he did basically he did a systematic review about image based Android malware detection. So he was focused on Android, not other systems.
okay.
Yeah, and he focused also in image based detectors for Android ecosystem or Android systems. He was looking at what are the approaches, the existing approaches used in literature first. Now, second, he was looking at what are the characteristics or what are the parameters or features that this mechanism did use by the authors. And now he was also criticizing the ways that this author did their work, I would say like that. And of course, he realized that the main work that have been done before, first of all, they mainly took the images as input, directly to the deep learning techniques to find results. Second, he identified also the fact that the authors, mentioned in their work these dimensions issues. They used to set the dimensions, okay, to give to these deep learning techniques. Third, he also found that some authors, including us, because we also did some research before, try to pre-process this image and found that it's possible that to have better results, than just having applied these deep learning techniques. And based on that, one of the future direction was also to now look into possible technique that can be investigated to improve results. That's why he moved into this work. Okay, he moved into this work that investigated on this approach. He investigated a lot of approaches, in fact. Okay, and that we retain just this Hilbert because this gave us interesting results.
Okay. Okay. Maybe we have one last question from Honoré. Are apps with vulnerability confused with malwares? So it
Apps
seems,
with.
yeah.
Mhm.
Is there a
Yeah, can you?
difference between vulnerability and when is an app said to be vulnerable?
Mhm.
Or maybe because the
Uh,
question is more like Apps with vulnerability confused with malware. It's more like, can some malwares be maybe difficult to detect, like very intelligent and difficult to detect?
Hello?
Yes.
Hello?
Yeah.
Can you get
Yes.
me?
Yes.
Apps
Absolutely.
very confused with numbers. Hello?
Yes,
Yes.
Benedict, we can hear you.
I'm seeing
Maybe
a
you want
hello, can
to.
you get me? Yeah,
Yes.
I'm seeing the question on the screen. Are apps with vulnerability? My network is really unstable. Are apps with vulnerability confused with malwares? That's the question. I don't know if Prof has already addressed that, or I should say something about that.
I can, or you can. You can say something you want.
Okay, Prof. Okay, Prof. Yeah, but I think that the issue of apps with I will not say that an app that has a vulnerability is a malware, because the vulnerabilities are just like holes. When you build a house, if you have several entries, or you leave maybe several openings, that does not make you a house with maybe with with doors that are open does not make it a malicious or a bad house. No, vulnerabilities are just like holes to uh, softwares that can be exploited. And I don't agree with the fact that apps that have vulnerabilities are necessarily malwares. We can have benign apps that have been built, but with a lot of vulnerabilities, and that's what we see today.
Yes, what I can say, hello. What I
Yeah.
can say is that, yeah, when you have a vulnerable app, you can now we need attackers need payload. They need payload to to infiltrate into this app now to launch the attack. So you can have vulnerable app that cannot get to an attack. You see the difference. This is what I want to outline. You can just have vulnerable app, but it's risky to have vulnerable app because an attacker can take advantage of to infiltrate a payload that will launch an attack. Yeah.
Okay. Um, we have a final comment from Idris that says IoT Data Malware 2023 is a document that can help. I don't know if you know that document, but maybe you can check it online, I guess. Thank you, Idris. I don't know. Prof, can you get me? Can you hear me?
Yeah, my dear, I'm there.
Okay. I don't know if there are any questions because I don't see any coming in the comment section. If there are none, then maybe we can wrap it up here. So we have been online for 2 hours, 3 minutes. Um, I don't know if, Prof, you have a final word for the audience. And yeah, also maybe I had the impression Idris is somehow very versed with the topic. Maybe yeah, you can reach out to Prof or to Benedict, or they can reach out to you for, I don't know, maybe you guys can work together because it's the whole idea of the KmerAI
Yes,
group.
yes, yes. I think also one of the vision of your of KmerAI is to put people together, right? So it
Yeah,
will also great for the community to scale.
exactly.
Yeah. We open it, and it was a great pleasure for us to participate. Yeah, and yeah, I think that we continue to make it permanent like that. Maybe, you know, this was the first time for me, for my team to participate, and I will be glad also to continue like that. And why not to have collaborators and collaborations from this, from your initiative. It's very interesting. It's very
Perfect.
And what I can add is that I will be in Morocco in 3 days, and what has been asked to me is to make the point to see what has been done in Cameroon concerning AI. And also, I think I will be glad to, to mention what KmerAI has been doing for long, so that they know and they can get in touch with you to have some details. It will be great.
That is absolutely perfect.
Yeah.
And yeah, do not hesitate if one of your students or even you want to present their work, because we really want to give people an audience where they can present their work and receive, like today, some interactions, some appreciations, and yeah, some collaborations. Why not? So please do not hesitate to reach out if you want to present your work.
Yes, I will be glad to present next week, huh? Another subject. No, why not?
That's very nice. So for next week, actually, we already have a presentation plan, and please be there because it will be very interesting. It's
Yeah.
on language models in biotechnology. So language models for identifying enzymatic binding sites, in protein sequences. So
Wow.
please be there for next week and invite your students, invite people, because yeah, why not? People can collaborate. And yeah, maybe the week after we can plan with you, Prof.
Yes, yes. Oh, it'll be a pleasure. It'll be a pleasure.
That's very nice.
Mm-hmm.
So if there are no other comments, so we will call this a day and see you all next week for a very interesting interaction. Goodbye.
What's the day? Can we have the schedule?
Oh, okay, okay, Prof. Normally presentations are always on Saturdays at 7 p.m. GMT plus 2. So that is
Okay.
6 p.m. Cameroonian time. If I, let's say,
Okay. Okay.
yeah,
7 p.m.
7 p.m. GMT plus 2.
Okay.
No. Sorry. I made a
It's
mistake. 7
7
p.m.
p.m. Cameroonian
Yeah,
time.
yeah, 7 p.m. Cameroonian time. My time is 8 p.m. Sorry.
Yeah, no problem. Understood.
Yeah. So actually, we will better, because we have a website where we have a website where previous presentations are, and then the plan is to add the schedule of the future presentations. So maybe we can work on that so it's easier for people to check online to see what's the next presentation and when it's coming. Another thing
Yeah.
is that depending on the presenter, we can accommodate for the time, because yeah, ideally we do not want someone to feel uncomfortable while doing his or her presentation. So,
Mm-hmm.
but ideally we want to keep the same day and the same time for consistency. But yeah, we are flexible and open.
Okay. Well noted. Well noted.
Thank you very much for the
You're
session of
welcome.
today, and see you next week.
See you.
Thank
See
you.
you. See
Bye.
you. Thank you a lot.
Bye bye. Bye bye.
So, are you waiting for? So.